More than half of Israel's territory lies in arid or semi-arid conditions, and in the south stretches the Negev Desert, where rainfall is scarce, temperatures are high, the ground is dry and rocky, and water has always been one of the greatest limitations on agriculture. Looking at the Negev from satellite imagery, it is difficult to imagine fish farms, green fields, advanced water treatment systems, and modern food production operating in such a place. That is exactly why I wanted to make this video. My goal is not to praise one country or present technology as a miracle. I want to share farming and aquaculture methods that may give difficult regions more options, especially places facing water shortages, saline soils, extreme heat, or environmental conditions where conventional agriculture struggles. For many years, when people talked about restoring dry land, the most obvious response was to plant more trees. Israel also invested in greening parts of its dry regions. From the air, forests against a brown desert landscape can look impressive, but deserts are more complicated than simply adding trees. Trees require water, suitable soil, and protection from heat stress, drought, pests, and fire. This does not mean planting trees is wrong. It means that in an extreme environment, relying on only one solution can be limiting. In the Negev, one of the most important answers was not found on the surface. It was hidden far beneath it. After the establishment of Israel in 1948, geological and hydrological surveys were carried out across the Negev. Scientists discovered ancient underground water reserves beneath the desert. But this was not ordinary fresh water that could simply be pumped up and used immediately. It was brackish groundwater with moderate salinity, and in some areas, geothermal characteristics. According to the material used for this video, salinity can be around 3 to 7 parts per thousand, while water temperatures at the surface can range from roughly 37 to 41 degrees Celsius. This water is unsuitable for drinking and is not ideal for directly irrigating many conventional crops. In the early stages, it was mainly studied for agricultural use. But researchers eventually began asking a different question. Instead of asking only how to remove all the salt and turn this groundwater into ordinary fresh water, scientists asked whether there were organisms that could thrive in the water as it already existed. That shift in thinking is important. Technology does not always mean forcing the environment to adapt completely to human needs. Sometimes the better approach is to understand the available resource and then choose species and production systems that fit it. If you are interested in models that turn an apparent disadvantage into a productive resource, stay with me until the end, because this story goes far beyond simply growing fish in the desert. From 1979 onward, research into desert aquaculture in Israel began to develop more systematically. Fish and other aquatic species were tested using brackish groundwater in the Negev. Tilapia became one of the species known for its adaptability, while other brackish water species were also studied. By the late 1980s, researchers at Ben Gurion University, including Professor Samuel Applebaum, helped demonstrate that desert aquaculture had potential beyond laboratory experiments and could move toward commercial production. Research centers dedicated to desert aquaculture helped transform an unusual idea into a structured production model. Of course, the process is not as simple as drilling a well, pumping up water, and adding fish. In some locations, groundwater can be extracted from depths of approximately 550 to 1,000 meters. When it reaches the surface, it can be close to 40 degrees Celsius. So, one of the first technical steps is temperature conditioning. Water can pass through holding tanks, heat exchange equipment, or cooling systems to bring it down to roughly 26 to 32 degrees Celsius, depending on the species and farm design. What is interesting is that all of the salt does not necessarily have to be removed. If the salinity falls within a range suitable for the farmed species, the natural characteristics of the groundwater become part of the production environment rather than something that must be completely eliminated. But in a place where every unit of water matters, using that water once and then discharging it would solve only part of the problem. This is where recirculating aquaculture systems, or RAS, become important. Instead of continuously bringing in new water and releasing old water, water from the fish tanks passes through treatment stages and then returns to the tanks. In well-optimized systems, a very large percentage can be reused, and the materials summarized for this video mention levels reaching up to around 99% in some systems. Think of the water as moving through a continuous cycle. Fish consume feed. Part of that feed becomes growth, while the rest eventually becomes waste. Fish feces, uneaten feed, and suspended organic particles are carried by the water. The first stage is mechanical filtration, where solid waste is captured. But removing visible particles only solves part of the problem. Dissolved compounds remain, especially ammonia produced through fish metabolism. If ammonia builds up beyond safe levels, it can become dangerous to the animals. This is where the biofilter begins to work. Biological filter media provide a large surface area where beneficial bacterial communities can grow. These bacteria participate in nitrification. In simple terms, ammonia is converted into nitrite, and nitrite is then converted into nitrate. Nitrate is less toxic to fish when kept at suitable levels and can also become useful to plants. Something that begins as fish waste does not necessarily have to end as useless waste. After mechanical and biological filtration, oxygen must also be restored. Fish need dissolved oxygen, and the microorganisms inside the biofilter also depend on suitable oxygen conditions. So the water is aerated or oxygenated before returning to the fish tank. Reduced to a simple diagram, the cycle looks like this. Fish tank, mechanical filter, biological filter, oxygen, and back to the tank. The engineering challenge lies in controlling temperature, oxygen, waste concentration, stocking density, water flow, and microbial activity. But the basic principle is simple. If water can be treated and safely reused, there is no reason to waste it after a single cycle. This becomes even more valuable in regions facing severe environmental limitations. Even a recirculating system must remove some water and accumulated nutrients to maintain balance. Instead of treating that stream as the end of the process, integrated aquaculture and agriculture can treat it as a new input. Water leaving the fish system may contain organic compounds and nutrients from feed and fish waste. With proper management, that water can be redirected toward agriculture. Drip irrigation is particularly useful in water-scarce areas. Rather than flooding the ground or spraying water across a large area, narrow irrigation lines deliver water directly toward the root zone. According to the materials summarized for this video, aquaculture water can support crops such as date palms, olive trees, alfalfa, and cherry tomatoes. This is the principle behind integrated aquaculture agriculture, connecting fish production and crop production within the same resource cycle. If you live or work in an area affected by water shortages, saline soil, extreme heat, or very dry land, tell me about the conditions in your region in the comments. The point is not to copy an Israeli farm exactly, but to ask whether local resources currently considered unusable could serve another productive purpose. Israel has also addressed another major water source, domestic wastewater. Water from showers, sinks, toilets, and urban households can be collected instead of simply being discharged. In the Tel Aviv area, large volumes of wastewater are sent to the Shafdan treatment system. Mechanical treatment first removes debris, suspended solids, sludge, grease, and other unwanted material. Biological treatment then uses microorganisms in aerated basins to break down much of the organic matter. Once again, microorganisms become an essential part of a carefully designed technological system. After biological treatment, one of the notable methods used in Israel is soil aquifer treatment, or SAT. Treated water is directed into infiltration basins with sandy soil. From there, it slowly moves downward through layers of soil and sand. During this process, physical, chemical, and biological mechanisms provide additional treatment. The water can then be stored in a suitable aquifer before being recovered for reuse. Where deeper treatment is required, additional technologies such as membranes, ozone, or ultraviolet treatment may also be used depending on the required water standard. The result is that water once described simply as urban wastewater can return to agriculture. According to figures summarized for this video, Israel reuses close to 90% of its domestic wastewater and is among the world leaders in this field. Think about the life cycle of a single cubic meter of water. It is used in a city, enters the sewer system, is collected and treated, then moves through a distribution network and may eventually reach the roots of crops growing in an arid region. So the water challenge of a dry country is not only about finding new sources, it is also about extending the useful life of the water already available. This is why I do not want this story to be reduced to the phrase, "Israel grows fish in the desert." The fish are simply the most visible part. The deeper lesson is that a resource unsuitable for one purpose can still be valuable for another. Brackish water may not be suitable for drinking, but it can suit certain aquatic species. Water leaving a fish system can potentially support crops. Treated urban wastewater can return to agriculture. The more often one process can safely provide an input for another, the less pressure there is to constantly search for completely new resources. The Negev also has another abundant resource: sunlight. With a high number of sunny days each year, the region is well suited for solar energy systems. Solar electricity can support pumping, aeration, filtration, monitoring, and other parts of modern farming operations. This illustrates the same principle again. Intense sunlight may make agriculture more difficult, but it can also provide energy. Brackish water may be unsuitable for drinking, but it can become a production resource. Extreme environments do not necessarily lack resources. They often contain a different combination of resources. From the aquaculture research that began in 1979 and the stronger commercial development that followed in the late 1980s, knowledge developed in the Negev gradually moved beyond Israel. By the late 1990s, and particularly during the 2000s, Israel expanded international training, technical knowledge transfer, and the commercialization of equipment such as biofilters, aeration systems, and water management technologies for dry regions. But when a technology moves into a new environment, it cannot simply be copied component by component. Water chemistry, temperatures, soils, energy costs, target species, and markets all change. The principles may remain, but the engineering has to be adapted. Australia is a useful example. Israeli water and aquaculture technologies, including biofilters and aeration solutions, have been commercialized for dry countries such as Australia. But Australian conditions are different from the Negev, so local systems can use their own advantages, including seawater access, intense sunlight, and greenhouse food production. The core idea remains efficient water use and environmental control, while the actual system is redesigned around Australian conditions. China provides another example of adaptation. In Xinjiang, aquaculture is being developed in areas around the Taklamakan Desert, far from the ocean. Some locations have saline and alkaline soils and water. Instead of treating these environments exactly like the Negev, local systems adjust mineral composition, control temperature, and create water conditions suited to different aquatic species, including Pacific white-leg shrimp and grouper. The lesson is not that China simply copied Israel. The more important point is that a similar way of thinking can be adapted to very different environments. Understand the local resource first, then build the production system around it. This is how technology transfer should be understood. Israel can contribute research experience, water management knowledge, biofiltration, recirculation, and experience with aquaculture in arid environments. But when a solution enters another country, it must change. Different water chemistry requires different treatment. Different temperatures require different conditioning. Different species require different salinity, oxygen, and nutrient management. Different energy prices change the economics of the design. The real value is not a single machine that works everywhere. The real value lies in the principles and in the ability to adapt them. If you think this approach is useful, share this video with someone working in farming, aquaculture, or living in an area with difficult environmental conditions. A model may not be directly suitable for their location, but seeing a different solution can help people begin asking better questions. Is there a local water source that has been ignored because it is unsuitable for conventional use? Can water move through more than one production cycle? Can aquaculture, crops, and energy be connected into a more efficient system? These are the questions I want this video to encourage. It is also important to be clear that technology does not remove every difficulty. RAS requires capital, energy, monitoring, and skilled operation. Brackish groundwater chemistry varies enormously from one place to another. Reclaimed water used for agriculture must meet appropriate safety standards. A model that works economically in Israel may not automatically be profitable elsewhere if energy prices, infrastructure, market demand, or operating costs are different. The purpose of studying these models is not blind imitation. The purpose is to increase the number of options available when designing solutions for difficult regions. Perhaps the biggest lesson from the Negev is not that humans somehow defeated the desert. A desert is not an enemy that needs to be defeated. What is more interesting is how people observed the limitations of the environment and designed production systems within those limits. Brackish groundwater is used for suitable species. Water is recirculated instead of used once. Bacteria process dissolved waste. Nutrient-rich water from aquaculture can continue toward crops. Urban wastewater is treated and returned to agriculture. Sunlight can provide energy. At each stage, the same question appears: can the output of one process become the input for another? If you want me to continue researching farming systems used in deserts, saline lands, water-scarce regions, or places with extreme climates, subscribe to the channel and leave the name of a region you want me to investigate in the comments. I want to build this series into a library of practical ideas so that people facing difficult environmental conditions can see more than one possible path instead of assuming conventional agriculture is their only option. Because in the end, a place that appears to have almost nothing may simply have resources that are harder to use. Its water may be brackish, its soil may contain too much salt, its climate may be too hot for familiar crops. But if we understand exactly what that place already has, choose the right species, use the right technology, and design the right resource cycle, an environmental disadvantage can sometimes become the foundation of an entirely different production model. And if approaches like these can give difficult regions one more option and reduce pressure on water, food production, or local livelihoods, then that is the real value I want this video to deliver.